We're getting a little bit of a late start today, but a couple of items of business. Next week, which will be the 3rd of March, I won't be here. Just a reminder. So the material to be covered there is in the schedule of the syllabus. And it indicates that you need to review the material that we're going to cover today. There's a video in Brightspace for you to use as a review. And also, we had been scheduled to do a lab on Le Chatelier's principle. That's lab number 3. This is an informal lab. So all you need to do is print out the hard copy from Brightspace and then go into that module that has the Le Chatelier's principle, lab number 3, and view the demo, the one where I do all the busy work in the lab, and complete the hard copy and turn that in. Then the next date coming up is March 6th. So it'll be the Monday after that Friday that I'm missing. Midterm grades are due, so I have to turn those in. So if you're missing any items, go into Brightspace and look at your grades and compare them to the syllabus and the due dates in the syllabus, and you'll see whether you're supposed to have something turned in. If there's not a grade there, that probably means I don't have it yet. So we need to check to be sure that I have everything I need, so that you'll have all the grades possible to be averaged in for the midterm grades. And then I'll be back on the 10th of March. And on the 10th, we'll have an exam on this material from today, chemical equilibrium. And we'll get the acids and bases chapters. My chapter 14, 15, and in Brown, it's chapter 16, and the first part of chapter 17. So we'll get those materials in, and we'll be back on schedule then. We won't have a lab on that day, right? On exam days, we don't have labs. Okay. If you have any other questions, contact me by email or text, or email is good. If you go into Brightspace, you can go into the class list and check off those who you want to send an email. If you want to send one to me, just check my name and send an email. If you need quick turnaround, then text me. All right. So let's take a look at chemical equilibrium. I need to share PowerPoints. Let's see. Share. As soon as this thing wakes up, here we go. Share. There we go. Okay, let's make a slideshow out of it. And get my picture out of the way. There we go. Chapter 13, my chapter 13, your chapter 15, in Brown. Chemical equilibrium. We, last chapter, we studied chemical kinetics. And the reason we did that first is because chemical equilibrium is better understood if you have a grasp of the speed at which a reaction occurs. Then equilibrium makes more sense. Historically speaking, though, the scientists that were working on chemical equilibrium and chemical kinetics were working on them almost simultaneously. But the mathematics for chemical equilibrium was less rigorous and less cumbersome than kinetics. And the theory behind it was a little better understood. So chemical equilibrium, that branch of chemistry, matured quicker than kinetics. But once we have an understanding of kinetics, then equilibrium makes a whole lot more sense. So for that reason, we studied kinetics first. What we have to understand is that by definition, a chemical reaction is at equilibrium. Say we have reactants and they make products. This reaction is considered at equilibrium when you don't see any change in concentrations of the reactants and products. In other words, they appear to be static. They may not start out that way, right? We learned that from kinetics. If you start out with this much and you don't have any products, then it's obviously going to go that way. But once equilibrium is reached, then macroscopically, what we observe is that the concentrations of the reactants and products now are static. But on the microscopic level, the activity is running at a furious pace. In other words, you're getting A and B combining to make C and D up here, and there would be a rate constant, right? We could write the rate law for that with a rate constant. But at equilibrium, the reverse reaction would be equal. The forward and the reverse rates of reaction. I should say these two are not equal, but the rate of the forward and the rate of the forward and the rate of the reverse are equal. Okay, that's when you have equilibrium on the atomic level, on the molecular level. It's what's known as dynamics. Dynamic means motion, static means no motion. So it appears to be static, but underneath we have a dynamic situation. That's what that slide means. Now, what we will observe based on concentrations is that for this particular reaction, nitrogen plus hydrogen yields ammonia. This is my favorite reaction, Haber-Bosch. You start out with a certain amount of hydrogen here and a certain amount of nitrogen and absolutely nothing of ammonia. That's at the very beginning. Then the ammonia gradually increases and the nitrogen and the hydrogen decrease. Notice that the hydrogen is decreasing at a faster rate because it takes 3 hydrogens for every nitrogen. So the nitrogen decreases at this rate, but the hydrogen decreases at a faster rate based on the stoichiometry of the reaction. But eventually, when we reach equilibrium, they're all steady at those concentrations. Now, those concentrations can vary. It all depends on what do you start with. Do you start with very high concentrations of nitrogen and hydrogen, and then you come down to a certain level, and ammonia, you come up to a certain level, then those concentrations may not be the same each time you run the reaction, depending on where you start. If you start at a high level, then the equilibrium is going to be established at a higher level than it is if you start at a low level. Right. I'll say more about that in just a minute. Okay, this reiterates what I've just said. When the concentrations are static, that means the forward reaction and the reverse reaction are occurring at exactly the same rate. This is just another way of looking at it. The forward rate, of course, is very high. The reverse rate is 0 when you start. because there are no products. You can't have a reverse reaction without reactants for the reverse step. But eventually their rates become equal. Okay. For this reaction, let's say we have, we're going to react water with carbon monoxide, and it produces hydrogen and carbon dioxide. Those are all gases, so I'm not going to write a little G next to them. All right. Let's say that we've reached equilibrium. Right? Doesn't matter where we started from. Eventually, we reach equilibrium in a closed vessel. Now, what would happen if you add more water? Right? If you add water, well, think about it. If you increase the concentration from an equilibrium position, now you've got more water available to interact with the carbon monoxide. So obviously, you're going to get some more an added reaction here that sends the reaction in this direction until you got enough of these over here that they catch up with their reverse reaction. And then we reestablished equilibrium. Right? So what we have done is when we add this, we consume some of it. Then we have to consume some of that. And we make some more of this and this until we have reached the same rates of forward and reverse reactions. What if we add more hydrogen, though? Instead, we're at equilibrium and we add more of this. Right? It's the same situation. I mean, it's the same understanding. It's the same explanation. It's a different situation, but the same explanation. You've added more of this. Now you have more of these to interact with what's available, and the reaction goes this way until you get enough of this product side, reactant side, so that you balance the rates again. Okay. So what came out of the research that was done on equilibrium was what's called the law of mass action. Now, the scientists that are given credit for this, Waage and Goldberg, were Norwegian scientists. And it's an interesting fact. In 1864, we still had, let's see, 1864, we were just coming out of the Napoleonic era. So Europe was in turmoil, and it was difficult for many scientists to pursue their research projects. But further north in Scandinavia, they were sort of isolated and insulated from a lot of the European problems. So at this time, there was a good bit of research being done and progress being made in Sweden and Norway on these chemistry issues. And these two fellows, they use different terminology and maybe different symbology, but it has come to the point where now it looks like this. Well, there's some, I'm jumping ahead of myself. They were interested, these two researchers were interested in deriving a mathematical description of chemical reactions and their equilibrium state. So they subdivided the activities into two sections. One was chemical dynamics, and that's what we call reaction rates or kinetics now. And the other was chemical statics, which we refer to now as equilibrium. Well, they had greater success with the chemical statics or the equilibrium side. And since they were working with solutions in their chemistry models, they expressed the mass action of the reactions in terms of concentrations. And molarity is the most common. So molarity is what you'll see most of the time, unless they're all gases, and then we have another option. If there are gases involved, then we have another option for expressing concentration, and that is partial pressures. We'll talk about that a little more in a few minutes. All right, this is the end result of this is the way we express it now. So if you have a reaction with a coefficient of little a and a little b for this reactant, right, and then you have products on this side, then the equilibrium okay, hold on a second. Let me mark present. Okay. This is 224. Okay, I got you down. I assume, did the test go okay?
Yeah, it finally worked. It took a couple.
I can't hear you.
Oh, Lord.
Well, you're not muted. Well, that's okay. Like I said in my email, if you have any trouble with with any of those individual problems, just send me an email with their identify each one gave you trouble, and I'll give you credit for them.
Okay.
Because I think porting things over from Blackboard to Brightspace has messed up this exam. Okay, so we were about 5 or 6 slides into this discussion of equilibrium, chemical equilibrium. And now we're at the point where we're quantifying the expression for chemical equilibrium. They found that if you take the concentrations, and we're going to use molarity here, the concentrations of the products, that's what we mean by square brackets. This is the molarity at equilibrium, the molarity of C times the molarity of D, and each one of these is raised to the coefficient power. That's in the numerator. Then in the denominator, we put the reactants. Like that. And that expression at a constant temperature. You can't change the temperature or you change the expression. So this is what's commonly called the law of mass action. And square brackets means molarity. Typically, though, we do not assign units to the K value. I mean, we could. Right? This could be molarity, 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 in which case, if these were all ones, 1, 1, 1, and 1, then it'd be molarity squared divided by molarity, so there'd be no units at all. But if we had powers in here, we could have just the sky's the limit. The units of measure would be unwieldy in many cases. So we typically, when we report a K value for an equilibrium reaction, an expression, we don't report units. We just be very careful about how we set it up. And then if we calculate the K, we may report the equation upon which it's based, And if you go to a reference manual, that's the way you'll see it. You'll see the equation and you'll see the K value, but there will be no units. There will be a reference, however, to concentrations. So if concentration is in molarity, that will be listed in the reference manual. If you're doing this instead of that way, if you're doing it partial pressures of gases, if the reaction is gas, 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 then you may have partial pressure of C times partial pressure of D raised to the C power to the D power. And then the rest of it down here. And then the reference manual will say concentrations in partial pressure. And it would have to say what units they are. Atmospheres is typical. That way, we get around having to put units on these things that could be just unwieldy. All right, so that's the general expression for the law of mass action for any balanced equation. There are occasions when we have to combine equations to like when we did thermochemistry, and I think that was last semester, and we have to combine equations for Hess's law. Then what do you do with the K value for the resultant equation? Well, if you have to invert the equation, if you have to turn it around the other direction and put the products and reactants and products, then this would simply be the new K would simply be the inverse. It'd be 1 over K. The new K for the inverted reaction would just be the inverse of the K. And it makes sense because now the reactants become products and the products become reactants. So you just put them in, the numerator becomes denominator and denominator becomes numerator. So that one makes a whole lot of sense. If, however, you have to multiply your whole equation by some constant value in order to make the additions come out right, then what does that mean? Well, if we have to multiply these by some value, say n, by the same n all the way across, right? If we do that, then this becomes NC, ND, NA, and NB, right? So we know from the rules of mathematics that this factor n can be brought outside. So now we have this expression, and it's all to the power of n. So that means the new K, K prime, I guess, would be the old K to the n power. Okay, those are transformations that sometimes we have to make with equations. And then this is what you do with the K value for equilibrium expression as a consequence of those manipulations. This is just restating, as long as the temperature doesn't change, the K will always be the same, no matter where you start. If you start with different concentrations and let it run to equilibrium, then the K will be constant if the temperature is the same as the K for which the K was developed in the first place. If you change the temperature, then you change the K. But if you don't, then the equilibrium, this is a true constant at a fixed temperature. However, if you start off at a higher concentration here, for instance, of reactants and let it run, then the final concentration at equilibrium will be different. Right? It'll use up enough of A and B to make C and D until you get forward and reverse reactions occurring at exactly the same rate. So that's known as the equilibrium position. If you start off at a different concentration, you end up at a different concentration, but it's still, the expression is a K, it's constant. So there's a difference between the equilibrium constant and the equilibrium position. We'll have examples here in a few minutes. Okay, so I think I can erase this one now. Let's see. K's can have subscripts, and some of them are dedicated to certain types of reactions. A general expression for equilibrium is often written KEQ. That could be anything. KW is a special equilibrium constant for water dissociation. We'll study that in the next 2 chapters after this, where we learn that water, pure water, can dissociate into these ions, and they will be in aqueous solution. Now, it doesn't make very many of them. It's a very small amount over here, but it is expressed as a K for a given temperature. So whenever we say KW, that always means equilibrium expression for water dissociation. Ka can be similarly written for acid dissociation. So if we have a generic acid like that, then it will dissociate into proton plus what's left over. So Ka always means acid dissociation constant. KSP, SP stands for solubility product. So if we have something like, I don't know, A and B, and it dissociates into A plus and B minus in aqueous solution, right? This will be a solid. Then we have an expression here, this K will express how far it goes to this side. Okay. Another one, Kf, is the formation constant for complex ions. We have a lab that we're going to do with complex ions where we complex silver ions with ammonia molecules, right? And we determine what that constant is. So we'll get more discussion about that later. But these are not the only ones. There are others, but those are the ones that we're going to be interested in. And then, of course, if we're using partial pressures, then we say Kp. That means the expression is partial pressure of our former reaction, partial pressure of C, partial pressure of D to the little c and the little d, and then partial pressure of A to the little a, and partial pressure of B to the little b. Okay. So that's the expression that would represent. Here's an example, the Haber-Bosch process, right, where you have product is ammonia. So we could either write it as molarity, right? You can have so many moles per liter, even as a gas. If you've got, say, a liter container, and you have 1 mole of gas in that liter, that's 1 molar of the gas in that container. Or you can write it as partial pressure, because partial pressure is proportional to the concentration, right? We learned that is partial pressure is proportional to mole fraction, which is another way of expressing concentration. So this particular equation could be written either way. The law of mass action for this equation could be written in terms of molarity or in terms of partial pressure.
Now, you don't always see parentheses here. Sometimes you just see the P with a subscript for its term, and then the power or the coefficient would be up here, and you won't see the parentheses. It's personal preference, whichever one. But when you see square brackets, that always means molarity. Okay. So what if we had partial pressures of, at equilibrium, we had so many atmospheres here of ammonia, 2.9 times 10 to the minus 2 atmospheres. Nitrogen and hydrogen would be those respective pressures in atmospheres. We could calculate the constant, the equilibrium constant for this reaction. The Kp for this reaction would be that expression. Those values, partial pressures in atmospheres, and the units of measure have to be the same, of course. You can't mix apples and oranges. And we get a value of 3.9 times 10 to the fourth. And that would be the equilibrium constant for that reaction in terms of atmosphere's partial pressure for each of the reactants and products. What if we knew that, but we'd rather have the expression in terms of molarity? Then we can use this equation. The equilibrium constant in partial pressures is this one times the gas constant, and this is the one with liter atmospheres in it, 0.08206. And this is temperature in Kelvin. And then up here, the power is what is the change in number of moles of gas from the reactants to the products. Right? So we take delta N then would be, and you could do this from the balanced equation. That's all you need. Just the coefficients on the balanced equation for the gases only. So you take the moles of product and subtract the moles of gas on the reactant side. So it's product minus reactants coefficients for the gases. And that would be delta N. So it could be positive number, it could be a negative number, right? In this case, in this example, I believe it's a negative number. See, 2 moles for the products, ammonia, minus 3 plus 1 or 4 gives you a minus 2. So that's where this power comes over here. That's minus 2. And there's your gas constant, and there's the temperature at 35 degrees. And here's the Kp that we just calculated, and here's the unknown. So we solve for that unknown, and notice you get an entirely different number when you're solving for molarity, molarity-based equilibrium constant versus atmosphere-based equilibrium constant, partial pressures. Okay, we've used this term before, homogeneous versus heterogeneous. So with respect to equilibrium, a homogeneous equilibrium is one in which all of the reactants and products are in the same state. These are all gases. So this Haber-Bosch process is a homogeneous equilibrium. Similarly, if they're all in aqueous solution, like this dissociation of hydrocyanic acid in aqueous solution, then that expression would also be a homogeneous equilibrium. And obviously, you're expecting the next slide to be heterogeneous, which it is. A heterogeneous equilibrium, then, is one in which there are 2 or more phases for the reactants and products altogether. Okay, we've got another attendee here. Okay. Notice that the first one, potassium chlorate, is a solid. And the products, potassium chloride is a solid, but oxygen is a gas. That makes this a heterogeneous equilibrium. Similarly, when we split the water molecule and make hydrogen and oxygen gas out of it, water obviously is a liquid and the products are gases. So that's a heterogeneous equilibrium. Now, one of the reasons for making this point is the way we treat these heterogeneous reactions in terms of calculating the equilibrium constant. And what we do is when we write the equilibrium expression, notice that equation, we would expect to write it something like this. Let's see, products, K would be KCl and O2, and then KCl would have a 2, this would have a 3, and then KClO3 would have a 2. Here's the problem. Concentrations for these solids do not change, right? They're just solids. They're not dissolved in anything. They can't change their concentration. They can go from, yeah, I'm here, until, no, I'm not, right? So these solids are not counted in the equilibrium expression, right? So we don't even include the solids. We only include gases and solutions. So aqueous, if it has a little g after it, or an aqueous, those are the only ones we count. If they're solids or pure liquids, if they're this one, that doesn't count either. So for instance, when I wrote that expression before, Kw equals, we would normally think of dissociating into this one and this one. And this would be, on the reactant side, that's a pure liquid. Doesn't count. So the Kw is actually that one times that one. That's it. Okay? Solids and pure liquids are not counted, are not included in the expression. Now, if that gives you a little trouble wrapping your mind around it, consider that these terms are buried in that term. Maybe that'll help. All right. So, can we draw any conclusions from just looking at the equilibrium constant relative to the reaction it is derived from, and say anything about where the equilibrium position tends to be? Well, let's draw this thing again. So we have C and D as our products, and reactants again would be A and B. Okay, so if this value is very, very, very large, what does that mean? If it's very large, that means that this term is very large and this term is very small. So that means the reaction wants to be to the right, or products. At equilibrium, you've got mostly products. So the reaction is said to go almost to completion. Whereas if the K is very small, see, this is large K. If we have small K, small K means that this is very small and this is very large, which means that the reaction would prefer to be on the reactant side and doesn't go very far toward the products. Okay? Now, textbooks tend to to jockey around the K as 1, greater than 1, or less than 1. The problem with that is the way we calculate K. You cannot be assured that the values here and their powers will give you a K of equal to 1 if you're basically equal on both sides. It doesn't work that way. All right. But if you're very small, less than 1, or very large, greater than 1, we can say some things about that. Let's see. So if the equilibrium lies to the right, the value of K should be very large because the numerator is huge. And if it's very small, then the equilibrium should lie to the left. We should have a very small K, or much, much less than 1. All right. Now, before we can actually use this to work problems and actually determine what concentrations there are, we can predict, or we can generate. If we know the concentrations at equilibrium, we can calculate a K. But if we're not at equilibrium, sometimes we need to know which way is the reaction going to go. I mean, with the concentrations given of reactants and products, if we start off with some of each, then which way is it going, this way or that way, right? We need to know that to solve problems. So we came up with a reaction quotient, Q. So what you do is with Q, you're not at equilibrium. So what we're going to have is product side, C, and D. Notice we use parentheses, not square brackets. With parentheses, we mean we are not at equilibrium yet. And then the reactant side, so we write the equation exactly the same, only we recognize that now we're not using equilibrium concentrations. So once we calculate that Q, we can compare it to the K. And that will tell us which way the reaction is going to go, to the right or to the left. Now, obviously, if you've got reactants in there and no products, that's a no-brainer. It's going to the right. Okay, we're talking about if you have concentrations of reactants and products already when you start, but it's not at equilibrium, or maybe it is. This is one way to find out. Okay, so these are initial concentrations. First one is the easy one. If Q equals K, then those concentrations mean that you're already at equilibrium. It's very hard to do that because of measurement errors. Right? You may think you have the right amounts, but once the reaction gets started, it might go just a slight way to one side or the other. Now, what happens if Q is greater than K? Right? If Q is greater than K, how does it do that? Q would be greater than K if the products were too high and the reactants were too low. That means Q would be greater than K. In that case, which way is it going? It's going to the left. Right? You got too much product and not enough reactant, so it's going to shift toward the reactants until you reach equilibrium. And then, of course, if Q is less than K, it goes the other direction. Right? Because if Q is less than K, it means you don't have enough product and you got too much reactant. So it's going to go that way. All right. So let's use an example here. How am I doing on time? 2:30. Okay, we're good. Consider this reaction in which, I'll just write it out first. This ion, right, in aqueous solution is reacted with this ion, this ion in aqueous solution, and it forms a complex ion, and everybody's in solution. So these iron ions interact with the thiocyanate ions and produce this complex ion, 2+ aqueous. Okay. So notice that the charges, a minus and a 3+ gives you a 2+. So the charges are right. And we're told that 6 molar iron and 10 molar thiocyanate are mixed at a certain temperature, and at equilibrium, the concentration of the complex ion is 4 molar. So what we want to do from that data is calculate the value for this equilibrium constant. Okay, we're going to use a procedure called ICE. ICE. This means initial. This means change. And this means equilibrium. Okay? So I'll usually put a line here, and a line here. So initially, what did we start with? 6 molar here. 6 molar. And we started with 10 molar here, right? 10 molar. And what did we start off with this? 0. All right. This is initial conditions. We don't have any of that yet. We started here. But at equilibrium, we're told that the concentration of this ion now is 4 molar. Okay. Now, in order to calculate the K for this reaction, which would be KF, remember that KF? The formation constant for this reaction. What we need is a term here and a term here. So we can logically back calculate, right? If this is 4 molar, how did it get there? Well, we had to add 4 molar concentration, didn't we? That's the only way it could get from 0 to there. Well, if these are 1 to 1 to 1, then how did that change happen? Well, it had to use 4 molar from this one, right? And these are 1 to 1, so it had to use 4 molar from this one. Okay. So now that makes the equilibrium concentration here, since we used up that much, this one is 6 molar, and this one is 2 molar. Okay. Now we have equilibrium constants. All we need is the expression. Let's see. I'm going to write it over here so I don't have to squat down. So case of F is equal to the concentration of this one, the complex ion, to the first power, divided by the iron 3+ ion to the first power, times the thiocyanate ion to the first power. So we can fill in our numbers as this will be 4 molar. This would be 2 molar. And this would be 6 molar. I don't need to write molarity in there. So we're not going to keep the units anyway. All right. So we just need to do that calculation. 4 divided by 12, right? It's 1/3. Okay, 0.333. That's the KF for this reaction. There you go. So there it is on a slide by itself. And then when you do the calculation, you get K is 0.333. Now that we know the K, we can change the conditions and find out what their equilibrium concentration should be. I think that's the next slide. Yes. So now we want to start out at a different concentration, 10 molar. So we got a different equilibrium position this time, right? These values are not going to be the same this time because we're starting at a different place. So this is going to be 10, correct? Yep. Well, 10.0. Okay. And this one's going to be 8. And this one's going to be 0. Right? We're starting off with just the reactants. Okay. So now we want to know what is this equilibrium concentration over here. All right. There we go. When we get to this point, we've got to use algebra. We got to say and give it an unknown, an X value. We know that we're going to produce some of this, right? So we're going to add so much concentration there. That means that this one is going to lose that much, and this one's going to lose that much also, because they're 1 to 1 to 1. So that means this term is 10 minus X. This term is 8 minus X. And this term is X. So if we put those into the expression, we'll do it on this side. So KF is 0.333 equals this one, this value, X. And then 10 minus X times 8 minus X. Okay. Now, since we chose X to be the concentration of this thing right here, once we find out what X is, that's our answer. So how do we do it? Well, from here on, it's just algebra, right? Solving for an X. But notice what happens. When you multiply this binomial, you get a quadratic equation. And there's a trick that we can use sometimes, but it only works if that value is very small. Right? If it's large enough like this, then you have to solve the quadratic equation. And that's what has come about here. I'm not going to do that all on the board, but you set that equal to 0.33, and then you solve for the X. And remember, when you solve a quadratic equation, that equation, I keep it on the back of my calculator. It's X equals minus B plus or minus the square root of B squared minus 4AC, all divided by 2A. In order for that to work, you've got to write the equation correctly. In other words, the quadratic has to be the X squared term first, then the X term, then the constant term equals 0. Everything equals 0. Then you can solve, you can use, this is A, this is B, this is C. You can put it in that equation and solve for X. Notice, since you've got a plus or minus here, outside this square root, you're going to get two answers. One way you do the plus and the other way you do the minus. And then you have to make a decision. Which one of those makes sense, physically, chemically speaking, right? In this case, we got an answer of 15.99 or 5. So we say, okay, 15.99, if X is 15.99, how did it get there, right? You've only got 8 here or 10 here. You can't have 15.99 because there's not enough reactant to do that. So that first term goes out. You can't use it. But the second term is 5. That makes sense. Right? You can get 5 out of 8 and 5 out of 10. So that's how we solve this equation. Now, hopefully we'll have one in a few minutes that has a very small K value, and I can use that trick, so to speak, and save us the problem, save us the trouble of solving a quadratic equation. Okay. We would start off for this one, same equation, different starting points. So this is going to have a different equilibrium position. And I'm not going to go through it because it'd take too long to do it again. We find out that now, instead of 5 molar, these new conditions give you 3 molar as your complex ion concentration. Okay, this is just a reminder. When you're doing these equations now, remember when we were doing kinetics, we could not use the coefficients to derive a rate law. Right? An overall equation could not be used to give us a rate law. It could give us the terms, but it couldn't give us the orders. Right? The coefficients had nothing to do with the orders. Now that was slightly different for the elementary steps, but for the overall equation, you had to find out the orders empirically. But for equilibrium, you need a balanced equation because the coefficients do go into the expression of the K. So balanced equation is essential. That's the first step. Then you write the law of mass action or the equilibrium expression, and you eliminate all the solids, all the pure liquids, and you keep only gases and aqueous solutions. Those concentrations are the only ones that count. Then I would set up an ice table. That's a good place to start. That way you can keep everything organized. Your initial concentrations, right? List the initial concentrations. And then if you're given concentrations for both sides, I mean, everyone's got a positive concentration. Then you need to calculate the Q to determine which way the reaction is going to go. If any side has a 0 in it, say if we had 10 here and 5 here and a 0 there, then we know which way it's going. It's got to go back. It's got to make some of this. So you don't have to do a Q in that case. But if you've got concentrations for all the terms, then you need to calculate the Q to determine which direction. And the reason for that is, if it's going this direction, then you're adding stuff here in the change step and subtracting from this step. But if it's going that direction, this is the negative change and these are the positive changes. That's why you need to know the direction for this to work. Okay. Okay, so I already said that. Then you want to choose, look at the question, look at the problem, and see where's the answer, right? Is the answer over here, or is it here, or where is it? And then if at all possible, choose the X, the unknown, so that when you solve for X, you get your answer. That's not always possible, but if it is, choose that X so that it gives you the answer. If you can't, then once you find the unknown, then you have to go back into your expressions and do a calculation to find the answer. Sometimes that's unavoidable. Then you substitute your values into the equilibrium expression and solve it for the unknown. And if you have to, use the quadratic. Right? There are examples that I'm not going to subject you to these. Some produce cubic equations. Some produce 4th power, 5th power, 6th power equations, those polynomials. If they do that, then I think there's a cubic expression like the quadratic solution. But once you get past that, they're just way off the wall. And then you have to use a process called iteration, in which you just pick an answer for X and then plug it in and see how close you are. And then use the values that you get out of that and put them back into the equation and run it again. And you keep doing that until you get closer to the answer. And there's a rule of thumb that we go by. If we have to do that, if we have to use iteration, then we compare the values that we get here. We plug them into the expression on this side and calculate a K value or a K value, yes. A K value for those numbers and say, is it close to the K value that we know? If it's within 5%, plus or minus 5%, then you can stop. You have your answers. All right, those are several of examples. I'm not going to go through all of them, but these are the answers that you should get out of the previous slide. If you run this example using the ICE method, then you should get these values. And notice they're different equilibrium positions, but it's still the same equilibrium constant. All right, so here we have decomposition of ammonia. All right, so we're running the Haber process in reverse. We're making ammonia into nitrogen and hydrogen. And this occurs at a certain temperature. And what we're saying for this example is we're starting with ammonia, 2 moles of ammonia in 1 liter container. Right? So it's a 2 molar concentration. Right? So if we do that, we have a marker that's not cooperating. Right? And that's going to decompose into nitrogen and hydrogen. Okay. Now, first thing we have to do is balance it. Right? Well, let's see, we need 2 nitrogens here. But now we need 6 hydrogens. So that's balanced. That's the first step. You have to balance the equation. And then what are the initial conditions? Right, we're starting off with 2 molar ammonia. And we're also told at equilibrium 1 mole of ammonia remains. Right? So change equilibrium. So at equilibrium, we know that 1 mole remains in the same volume. That means it's 1 molar. Okay, so how did it get there? Well, we had to subtract 1 molar, didn't we? Right. How about the others? What's the question? Calculate the K, okay. So the relationship here says that, and these are 0. The relationship says that for every 2 of these, you get 1 of those. So this is going to be a plus 0.5 molar, right? It's just half as much. And this is going to be 3 times that. So this would be plus 1.5 molar. Okay, so now we know that this is 0.5 and this is 1.5. Now we can calculate the K. We just have to set up the expression, right? Nitrogen to the first power, hydrogen to the third power, and ammonia squared, right? So we can plug in our numbers. Let's see, nitrogen is 0.5, hydrogen is 1.5 cubed, and ammonia is 1 squared. Okay, that sets up the equation and we can solve for K. Let's see here. Next slide. Oh, it went ahead and did the math for me. We should end up with 1.69 as our K value, which means what? Well, it's greater than 1. So it's kind of hard to tell, right? Greater than 1, you would expect it to be slightly toward this side, which makes sense. That's the way the Haber process works. It prefers to be over here and not over there. Here's another one. Okay, let's do this one. Let me check let me see how much more I have to do. I don't want to get bogged down. Okay, we're good. We're good. We can do this one. All right, so our reaction is N2O4. And that's a gas. Yeah, they're both gases, so I'm not going to write that in there. And this one is 2NO2. All right, and the K, we're told that the K is equal to 4 times 10 to the minus 4. So what does that tell you about the reaction? At equilibrium, it tends to be over here. This is very small, this is very large. Okay, so now calculate the equilibrium concentrations of N2O4 and that. All right, so we need our ice table. And our starting conditions, 1 mole sample of N2O4 in 10 liters. So that's 0.1 molar. 1/10, right? 1 mole in 10. And nothing here. Okay, so we know it's going this direction. We're going to add a certain amount. Let's see. I'm covering up something. Let me be sure I'm not missing any data. Okay, we're good. Calculate the equilibrium concentrations. All right. So we're going to have to use X's. We know that we're going to produce, if we lose an X over here, we're going to produce 2 X's over here because 1 to 2. So this expression is going to be 0.10 minus X, and this is going to be 2X. Okay? So the expression is NO2 squared over N2O4 to the first power. So we plug in our numbers, right? We have 2X squared, and then we have 0.10 minus X to the first power. Okay? Oh, and that's equal to 4 times 10 to the minus 4. And if we solve for X, then 2 times X is this concentration, and 0.1 minus X is that concentration. All right. So notice that the K is very small. So the change, we're only going to lose a very tiny amount of this and produce a very tiny amount of this over here. So we can use an approximation. We're saying that X is so much smaller than 0.1 that we can ignore it. So we're going to say approximately, let's go ahead and square this one. 4X squared over 0.10. We just drop that X out. And that's equal to 4 times 10 to the minus 4. Okay, now we can solve for X. Very simply, we just say this times that. So X equals the square root of 0.10 times 4.00 times 10 to the minus 4 divided by 4. So I just took this one over here times that, this one over here divided by it, and then to get X, I just took the square root of both sides. That's where I came to this expression. So now we should be able to calculate that fairly quickly. Let's see, 4 exponent 4 to the minus, and then 0.1 times, and divided by 4, and then take the square root of it. Let's see, 0.0032. Okay, so what does that mean? That means that 0.1 minus that number is 0.0968. Molar. And this would be 2 times that number, which would be 0.0064 molar. So we were basically right. There wasn't very much change, right, to go from 0.1 to 0.09, and not even that far. Okay. So let's see if that's what they agree with. 0.097, okay, round it off. And 6.32 times, yeah, 10 to the minus 3. Okay, so we're good. All right. Now, how do we know that that approximation was not a huge mistake? Well, we take these values right here, put them back into the equation here, right here. So we would calculate K using those values. Right. So NO2 squared is 0.0064 squared divided by 0.0968. Okay, put those values in there and do that calculation and see what kind of K we come up with. 0.0064 squared. And then divide by 0.0968. Oops. Divide. Let's see. Yeah, I get 4. I need some more decimal points because I think that's rounded off. That's truncated. So let me go in here and change my, let's see, where is it? Display. I want scientific, let's see, about 6 decimals. 4.23 times 10 to the minus 4. Okay. We got 4, and this is 4.23. So how do you tell if it's not too far away? Right? Because that looks like it's a long way off. So what's the difference? The difference is 0.23 times 10 to the minus 4. And you divide it by the accepted value. Times 10 to the minus 4 times 100. Okay. So what percent is that? Let's see, 4 exponent 4 there, minus, and then times 100. That's not right. 0.23 divided by 4, there, times 100. I got 5.75%. Okay, so my calculations say it's too big, just by a little bit. So what do we do? Well, you have 2 choices. You can either keep that x, generate a quadratic and solve it, or you can take the x value, put x right in here, not in there, just in here, because that's the one we removed. And then solve it again for x. That's called the iteration. That's the first step iteration. Sometimes it takes 2 or 3 times. But that should bring you down less than 5%. But we're in agreement with the slide, so I'm going to go ahead. We're going to move on. That just does show you that you can use these approximations sometimes, especially if this value is very small. All right. Now we come to Le Chatelier's principle. We sort of dabbled in it at the very beginning of this slide set. When we changed to concentrations and an equilibrium situation and what happens to it. Le Chatelier expressed this well, he gets credit for it anyway. He says, if a system is at equilibrium and we do anything to disturb its equilibrium position, then the system will respond in such a way as to mitigate that stress. In other words, it will shift to reduce the change. That just means in cases of concentration, if it's at equilibrium and you add any reactant, it will shift toward the products. Or if you add a product, it'll shift toward the reactant. Or if you remove product somehow, then it will shift to the product side. Okay, and that discussion is concentration. Changes in concentration are really, they're easy to rationalize. Oh, I got a movie here.
Le Chatelier's principle states that if you have a reaction equilibrium and you apply a stress to that equilibrium, the reaction will shift in a direction in order to relieve the stress. We will look at a series of different reaction equilibria. We'll apply a stress to those equilibria and see in which direction they shift. In the reaction between iron plus 3 ion and thiocyanate ion, if we add some iron plus 3 in the form of iron 3 nitrate, and to the iron 3 nitrate add some potassium thiocyanate, the two react to form a reddish-orange complex ion. We fill 2 test tubes with the reaction mixture. We're going to keep one test tube as a control so that we can see what happens to the color. To the other tube, we're going to add some 0.1 molar iron nitrate to increase the concentration of the iron. We see that there's an increase in the dark red color. This indicates an increase in the concentration of the complex ion. This also indicates that the reaction has shifted in the forward direction. As you add reactant to an equilibrium, the reaction shifts in the direction to use up the added reactant, in this case the forward direction. Now we'll add 0.1 molar potassium thiocyanate to the second tube. This increases the concentration of the thiocyanate ion. We see that the reaction mixture turns a darker red color, indicating an increase in the formation of the complex ion. We've added the other reactant, the thiocyanate. The reaction shifts in the forward direction to use up the added reactant. We will now add some 1 molar sodium hydroxide solution. We notice that the red color decreases significantly. This indicates that the reaction equilibrium has shifted in the reverse direction. The hydroxide ion precipitates the iron ion, effectively removing it from the solution. The equilibrium shifts in the reverse direction to try and increase the concentration of the iron. We will now add solid potassium chloride to the solution. We notice the decrease in color indicating that the reaction has shifted in the reverse direction. The chloride ion forms a complex ion with the iron, effectively tying up the iron concentration. The equilibrium shifts in the reverse direction to try and replace the iron that's been removed. We will now add 0.1 molar silver nitrate to the reaction mixture. We notice the disappearance of the red color, which indicates that the equilibrium has shifted in the reverse direction. We also see the formation of a small amount of white solid. The silver ion reacts with the thiocyanate ion to form slightly soluble silver thiocyanate, which is the white solid. The silver ion removes thiocyanate from solution. The equilibrium shifts in the reverse direction to try and replace the thiocyanate ion that's been removed. We will now add some 0.1 molar mercury 2 nitrate. The mercury plus 2 ion reacts with the thiocyanate ion to form a new complex ion. This effectively reduces the concentration of thiocyanate in the solution. The equilibrium shifts in the reverse direction to try and replace the removed thiocyanate.
Okay. As usual, when I process this video, I will insert the original so it won't be so fuzzy. But I want to make a point here. My markers, here we go. For this reaction, where the iron 3 plus and the thiocyanate produced this complex ion, and then some other reactions were used to change the concentrations of the reactants or products. For instance, let's use this one. Let's see. Yeah. So we had this complex, I think it was another complex ion. I forget how many there were, maybe 4. Right, so it'd be 3 minus, no, it'd be 1 minus 4. I think that's right. The point I want to make is this is what's called a coupled reaction. We coupled this reaction with that reaction to produce an effect in the main reaction. And that's basically what you're going to see in that lab, the Le Chatelier's principal lab. Lots of coupled reactions that are influencing the movement, the equilibrium in one of the main reactions. Now, when the questions arise in that lab, Le Chatelier's principle, if you're going to say the reaction shifts to the right or shifts to the left, then you need to have the balanced equation to reference. Otherwise, right and left means nothing. So you got to write out the balanced equation, and then you can say it shifts left or right, or you can say it shifts toward such and such a product and write out the name of it, or write out the formula. But you have to be, it has to be unambiguous. You can't leave anything to guesswork. If you're going to say it moves left or right, you need a balanced equation to do that. All right. So let's see what's next. Temperature. So what happens when we change the temperature? Well, actually changing the temperature actually changes the K. So the effect, the Le Chatelier principle effect, is actually a change in the K when we change the temperature. That's what's going on behind the scenes when we change the temperature. We're changing the K value and shifting the equilibrium based on the K. But it's useful when you have a reaction like this, for instance, another generic reaction. If you want to draw some conclusions, some qualitative conclusions about which way the reaction shifts, is if this reaction is exothermic, where would the heat term go? It'd go on the product side, wouldn't it? Because it's releasing energy. Energy that was potential and stored in the reactants is now separated from the products, and you have a separate term, your Q value or your heat. Sometimes they write delta H for enthalpy. If you put it on this side that way, now we can say something about the equilibrium shift. If we increase the temperature here what are we doing? We're adding a product and the reaction shifts back this way. That's exothermic. If the reaction is endothermic, then the heat is going in on this side. And for endothermic, if you increase the heat in the temperature, you're adding heat to the reactant side. Now it shifts toward the products. So that's a useful concept. Recognizing that it's not that simple. We're changing the K value is what we're doing. Okay. So that's temperature. I think I've got another video coming up. Yeah, here it comes. So let me start it.
This is MSJ Chem. In this video, I'll be looking at Le Chatelier's principle and temperature. Changes in temperature cause a change in the equilibrium position and in the value of the equilibrium constant Kc. Here we have the chemical equation for the Haber process. In the Haber process, nitrogen and hydrogen react together to form ammonia. The forward reaction of the Haber process is exothermic. This can be seen by the negative value for the change in enthalpy. If the forward reaction is exothermic, the reverse reaction is endothermic. We can see this by looking at the sign of the enthalpy change, which is positive. So when we use Le Chatelier's principle to predict in which direction the equilibrium position will shift, we need to know if the forward reaction is endothermic or exothermic. If the forward reaction is exothermic, the reverse reaction is endothermic, and vice versa. Next, we'll predict in which direction the equilibrium position will shift when the temperature is increased. When the temperature is increased, the equilibrium position will shift to the left, which is the reactant side. And the reason for this is that the system will absorb the extra heat, favoring the reverse reaction, because it is endothermic. When the temperature is increased, the reverse reaction will be favored because it absorbs heat. Therefore, the equilibrium position will shift to the left, in the endothermic direction. Next, we'll predict in which direction the equilibrium position will shift when the temperature is decreased. So when the temperature is decreased, the equilibrium position will shift to the right, which is the product side. And the reason for this is that the system will produce heat favoring the forward reaction, because it is exothermic. When the temperature is decreased, the equilibrium position will shift in the exothermic direction, which is to the right. Next, we look at the effect of temperature on the value of the equilibrium constant Kc. So for an exothermic reaction, increasing the temperature shifts the equilibrium position to the left and decreases the value of the Kc. So as we saw in a previous slide, the forward reaction of the Haber process is exothermic. Here we have the equilibrium constant expression for the Haber process. When the equilibrium position shifts to the left, the value of the numerator decreases and the value of the denominator increases. Therefore, the value of the Kc decreases. So an increase in temperature for an exothermic reaction results in a decrease in the value of the Kc. For an endothermic reaction, increasing the temperature shifts the equilibrium position to the right and increases the value of the Kc. Here we have the reaction between hydrogen and carbon dioxide to produce water vapor and carbon monoxide. As we can see from the sign of the enthalpy change, the forward reaction is endothermic. And here we have the equilibrium constant expression for the reaction. When the equilibrium position shifts to the right, the value of the numerator increases and the value of the denominator decreases. Therefore, the value of the Kc increases. So for an endothermic reaction, an increase in temperature results in an increase in the value of the Kc. So let's end with a summary, starting first with exothermic reactions. When the temperature is increased, the equilibrium position shifts to the left and the value of the Kc decreases. And when the temperature is decreased, the equilibrium position shifts to the right and the value of the Kc increases. And finally, for endothermic reactions. When the temperature is increased, the equilibrium position shifts to the right and the value of the Kc increases. And when the temperature is decreased, the equilibrium position shifts to the left and the value of the Kc decreases.
All right, before I talk about pressure, the Haber process, let's use that as our example. Let's see, 2, 3. If we look at this as an energy diagram, and remember this is reaction progress, and this is potential energy. We start off at a certain amount of energy for the reactants, right? This is your N2 and your H2. And then we need an activation energy, right? So remember this from kinetics, activation energy. And then the products are down here, right? It's exothermic reaction. This is delta H, which is a negative value, right? Okay. So notice that if we increase the temperature, let's see. All right, I'm trying to think the way Fritz Haber thought when he was devising this experiment. He needed to reach this activation energy here. Some solid line right there. He needed that much energy. So he had no choice. He had to increase the temperature, I think 800 degrees Celsius, to supply enough activation energy to get started. But in the process, he shifted the equilibrium back toward, toward the reactants. Right? So it was damned if you do and damned if you don't. So what he did was, instead of that, instead of making any other changes, he added a catalyst, which when he added the catalyst, he decreased the activation energy. Now he has the activation energy with the catalyst. In fact, his catalyst was very finely divided iron, pure iron. So it took less energy. So that meant that at that temperature, even though equilibrium was favored in reverse, he was getting more of the reactants to lead to products. So he was approaching the problem from two different directions, from the kinetics direction and from the equilibrium direction, and he found a compromise. So when he got some product over here, right? And remember, these are still, they're all in a mix, right? You still got these together with those producing the mix. So what he did was he bled off, right? He bled off part of this and ran it through a cooler. He chilled it. And the boiling point for ammonia is much higher than it is for nitrogen and hydrogen. So he only had to chill it a certain degree, and he got liquid ammonia, right? And then he took what was left over, ran it back through again, and he just kept this cycle going. So after about 4 or 5 cycles, he managed to get an efficiency of about 15%, right? Which was pretty good. Okay, now we can talk about pressure. Let's see. I can erase this. I'm going to leave that reaction because I think we're referencing this reaction again. So I'm going to leave it up there. And let's see, what's the effect of pressure? A change in pressure on equilibrium. Well, how do you change the pressure in a reaction vessel? Well, if it's any of the reactants and products are in solution, it doesn't matter. Pressure doesn't change their concentrations at all. Only if gases are involved. If you change the pressure on the gases, then you increase the concentration of the gases. If you and that's by decreasing the volume. So if you got this reaction vessel and you're not going to add anything to it, right? Because that's concentration change. We're talking about pressure change. So you'd have to squeeze it, decrease the volume, increases the pressure, right? According to Boyle. When you do that, the reaction is going to respond in a way to reduce the pressure. So how do you reduce the pressure? If all the reactants and products are gases, well, the side with the fewer moles, if you favor the side with the fewer moles of gas, you will reduce the pressure, right? Because you're reducing the mole fraction of gases, of each of the partial pressures of the gases. And when that happens, you reduce the pressure. So for this type of reaction, where we have 2 moles on this side and 4 moles on that side, if we increase the pressure, which side is it going to go? It's going to go that way. So that was another detail that I left out of Fritz Haber's process. He increased the pressure to something like 40 or 50 atmospheres in the reaction vessel. And that favored, by this Le Chatelier's principle, that favored also the product. Okay. If you introduce an inert gas, what effect does that have? Well, you can increase the pressure, but you're not introducing any more reactants or products, and you're not making them any closer together, right? There's no effective change in partial pressure for each of these components. So there's no effect whatsoever. Inert gases do not affect the equilibrium. If you decrease the volume, then you favor the side with the fewer moles. If you increase the volume, you favor the side with more moles. So if we increase the volume on our vessel, you'll favor that side in this example. All right. So we got another one with that same guy talking.
The pressure of a system can be changed by either adding or removing a reactant or product, or changing the volume of the reaction vessel. The first point has the effect of increasing the concentration of the reactants or products. The second point refers to Boyle's law. Boyle's law states that pressure and volume are inversely proportional at constant temperature. This can be written in equation form as P times V equals constant K. Changes in volume will affect the pressure of the reaction vessel. For example, if the volume of the reaction vessel is increased, the pressure will decrease. And if the volume of the reaction vessel is decreased, pressure will increase. It should be noted that changes in pressure only have an effect on the equilibrium position when there are different amounts of gaseous molecules in the reactants and products. So next we look at some examples. The reaction we look at is the Haber process, in which nitrogen and hydrogen react together to form ammonia. In this equation we have 4 moles of gas on the reactant side and 2 moles of gas on the product side. This means on the reactant side we have more gaseous molecules, and on the product side we have fewer gaseous molecules. When the position of equilibrium shifts to the side with a fewer number of gaseous molecules, this results in a decrease in pressure. And when the position of equilibrium shifts towards the side with a greater number of gaseous molecules, this results in an increase in pressure. So when we make predictions about in which direction the position of equilibrium will shift for changes in pressure, we need to consider the number of gaseous molecules in the reactants and products. So in the next example, we'll predict in which direction the equilibrium position will shift when the pressure is increased. An increase in pressure shifts the equilibrium position to the right, which is the product side. So the equilibrium position will shift to the right because there are fewer gaseous molecules on the product side, which lowers the pressure. As we saw earlier, there are fewer gaseous molecules on the product side of the equation. When the pressure is increased, the equilibrium position shifts to the side with a fewer gaseous molecules, which has the effect of lowering the pressure of the system. Just like for changes in concentration, changes in pressure do not affect the value of the equilibrium constant Kc. In our next example, we'll predict in which direction the equilibrium position will shift when the pressure is decreased. When the pressure is decreased, the equilibrium position shifts to the left, which is the reactant side. So the equilibrium position will shift to the left because there are more gaseous molecules on the reactant side, which increases the pressure. Because we have more gaseous molecules on the reactant side, an increase in pressure will shift the equilibrium to the left. And once again, the value of the Kc does not change. In our last example, we'll look at changes in pressure when there are the same number of gaseous molecules in the reactants and products. So in this reaction, we have 2 moles of gas on the reactant side and 2 moles of gas on the product side. So the position of equilibrium will not change because there are the same number of gaseous molecules on both sides of the equation. So if we have equal numbers of gaseous molecules in the reactants and products, changes in pressure have no effect on the position of equilibrium. So let's end with a summary. In this table, we have change to the system at equilibrium, change in equilibrium position, and change in the value of the Kc. When the pressure is increased, the equilibrium position shifts to the side with fewer gaseous molecules. When the pressure is decreased, the equilibrium position shifts to the side with more gaseous molecules. And changes in pressure when there's equal numbers of gaseous molecules in the reactants and products has no effect on the equilibrium position. And as we can see, the value of the Kc does not change when changes are made to the pressure of the system.
Okay, I think that's our last slide. Yes. Okay, so that one, he made one point that I didn't make, which is important, that if there are equal numbers of gas, moles of gas on both sides of the reaction, pressure has no effect on the reaction equilibrium. And the only time that the K value actually changes in any one of these scenarios is when we change the temperature. Change the concentration, change the pressure, then the K stays the same. All right. Okay, so just to bore you with details again, I'm not going to be here next week because I have a mandatory meeting at New River. So you'll be on your own with the review for this material between now and 2 weeks from today. And you'll also need to do Le Chatelier's principle on your own. I think what I'll do, I've got a review video that I produced in Beckley that's more recent than the one that's in the Brightspace right now. And I need to take a look at it, the one that's in there now, and see if the one I've just produced is better video quality, if nothing else. So it may shift over the next day or two. It may shift from the old date to the new date. And then when we come back on the 10th of March, we'll have an exam on this material, and I'll introduce acids and bases. And there will be no lab on that day. So I guess technically speaking, I've always said that the labs are due the next time we go in for a lab. So Le Chatelier's principle won't be due next time we meet. It'll be due the time after that when we come in for we'll do the Ka of acetic acid. All right, remember that different subscripts, the Ka of acetic acid. So we'll have acetic acid, and it'll be in equilibrium with these ions, right? And there'll be a K associated with it. And that's a pretty fun lab. We get to do a titration and use a pH meter to follow the progress of the reaction. So don't miss that one. I think you'll have fun with that one.